being one of the organizers, I'm not allowed to thank organizers. So instead, I will thank all our amazing participants who made this happen. Thank you. OK, so my talk is about six-vertex model. And we've seen a lot of it already in this conference. So I will just set some of the notations here. So these are same six vertices as I think Philippa had, but not quite so. But Philippe has something else today in the morning, right? So I will have 6 weights, A1, A2, B1, B2, C1, C2. So there will be 6 constants appearing here. I will be dealing with a model in some finite domains. So typically, I will have some coming paths, outgoing paths, and then the configuration will be somehow connecting all these paths together. I will be weighting configurations according to A1 to the number of A1 vertices, A2 number of A2 vertices, etc., normalized by some partition function to make this sum up to 1. And I will be speaking about the configuration in terms of the height function. And again, my height function is slightly different from the one which Promit used. So my height function, I think in Promit's height function, only when he moved to the left, it was growing by 1. But actually, in all directions, when you cross a path for my height function, your height will be changing by 1. So maybe you have kind of collection of 2s here. It's a value of the height function. If you move up from it, so cross the path, you convert to 3. If you move right through it, cross the path, you go to 1. In this way, well, it's defined up to additive constant, and you need to fix it somehow, and it will be kind of clear in those stations how do I fix it. So there are lots of histories here, and I'm not going to repeat this for this audience. The only thing which is important from the point of view of my talk is that six-vertex model is connections to many other models of statistical mechanics, such as dimers, domino and Lozenge tilings, XXZ spin chain, random cluster models, Kadar-Parisi-Jeanke equation. And we will see even more connections in this talk to hopefully new types of models that maybe you didn't realize before that's connected to these things. OK, so one of the central questions, at least from my perspective for the six-vertex model, would sound as follows. So you take some very large domain, and you say something about the boundary conditions, so how the paths should be entering and leaving it. And you fix your 6 parameters, A1, A2, B1, B2, C1, C2. And you sample your configuration according to this probability measure. And then you're trying to understand how will a typical random configuration look like, or how will the height function of this random typical configuration, how will it look like? So that's, for me, that's an important question about the six-vertex model. Now, in general, if you do simulations, they show that there is a very rich asymptotic phenomenology here. Well, for example, this simulation, these are for our favorite domain wall boundary conditions, and what's shown in blue is actually, I think, maybe C-type vertices, and you see that they form some interesting shapes here. So you can get many of these interesting pictures from the simulations, but when you go to mathematics, then turn out that outside the case where A1, A2 plus B1 plus B2 is equal to C1, C2, which is something called free fermion case, and it corresponds to dimers and to those limit shapes which Alexei, for example, was speaking about on Monday. So outside this very special case, we have very, very limited knowledge. So even for those domain wall boundary conditions, which, for example, Philippa was discussing yesterday, we don't know, this is the situation, but we don't know anything about this picture. You see that clearly, the densities are different part of the picture, but actually, we don't even have a conjectural expression for that. So that is completely open. And I think that's a fascinating question to find these limit shapes, try to say something about these limits.
You said we don't even have a conjectural question?
No, conjectural expression. So for
expression.
Right. For the limit of the height function. Right. So like Philippa can tell you what is the frozen boundary, like where the one behavior changes to another. But inside this frozen boundary, even Philippa can kind of tell you what should be there. Okay. So what is it today? So today I will tell about some new information that we managed to obtain in recent years, which is that we managed to obtain some answer to this problem, not in general situation, general is still wide open, but in somewhat degenerate situation when you start taking a limit in which these two weights, C1 and C2, corresponding to the corners in your domain, in your path, these two weights will be tending to 0. And in fact, other parameters will be all approximately equal to each other. So if you like this parameter delta of the six-vertex model, this delta will be approaching 1. And I will be telling you about two connected stories, one from my article with A.Borodin from 5 years ago, and another from my ongoing project with R.Kenyon from this year. So let's start with the early result, because it will connect us nicely to the talk which we just heard. So that will be about stochastic six-vertex model. So for the stochastic six-vertex model, we will be choosing the weights 1, 1, B1, B2, 1 minus B1, 1 minus B2. So there's two parameters here, B1 and B2. And for the boundary conditions, we will be doing something quite specific. So we will be looking at the n times n square. For this square, we will fix deterministically how the paths enter or not enter along the left boundary and how they enter or not enter along the bottom boundary. While on the top boundary and on the right boundary, we will not do any constraints. So we'll say that boundary conditions are free there. So we allow, if you want the path, will exit here. But if you want it will exit there, everything is allowed. So these are all possible configurations. And then we sample, model according to these weights and in this n times n square. So you get something that is one example of this configuration. So again, it's, here is deterministic, but on top and right boundary, it kind of becomes random because, you did not fix anything there. And again, we will be speaking about this configuration of the model in terms of the height function. For normalization, I will now assume that the height function is 0 in the bottom left corner. And then again, when you cross the path, it either grows or decays depending on direction, how you grow it. It is exactly the same as what Promit was speaking about, really the same stochastic six-vertex model. Okay, now I promised to you that I will be looking at the regime where the corners become rare. So where, these C1 and C2 parameters, which we have 1 minus B1 minus B2. So these will be the parameters which will tend into 0. Namely, how you will do it, then you will say that B1 is some number which goes to 1 at linear speed. So as your size of the square becomes large, so B1 will be exponent of minus beta 1 over n, and B2, well, exponent minus B2 over n. Then it's just, to fix some speeds with B1 and B2 goes to 1, and therefore C1 and C2 go to 0. And so 5 years ago with Alexei, we proved the limit shift theorem in this situation. So if the corners are rare and you analyze this model, then it turns out that if you look at the rescaled height function, 1 over n, h, and x, and y, then this random height function converges to deterministic height function, called small h here. And this deterministic height function in this situation can be found by solution of certain partial differential equation. Now the partial differential equation itself, it is best spelled not in terms of h, but in terms of q to the h, where q is a constant which kind of governs the speeds, beta 1, beta 2, how these things change. And so that's an equation in terms of this q to the h's. So you see there's a second mixed second partial derivative here and two first order derivatives here. And for this equation, you have some boundary conditions which are just, which encode how paths enter through this border and how paths enter through that border. And so you need to solve this hyperbolic PDE with these boundary conditions. Now this hyperbolic PDE, well, this has a name in the literature. It's usually called telegraph equation, although it's more often people use it in a different coordinate system like x plus y and x minus y. It's called telegraph equation. And this is something called characteristic Cauchy problem to find the solution of this equation given that you know what's happening on this direction and this direction. And there is a known formula that there is a unique solution given these two boundary conditions. It has some integral representation. Okay, so this map, q to the h, is kind of important to get in such a simple linear equation. Because if you don't use this map, then, okay, you can still write PDE for your height function, for the limiting height function, but it will be a more complicated one. So that's a PDE which you get otherwise. It's kind of have the same component, hxy, hx, hy, but also nonlinearity would appear, hx times hy. And of course, we all know that solving nonlinear equation is much harder than solving linear equation. That's why it's good actually to use this, map, to use q to the h, and then write the equation for the limit shape in terms of this q to the h. And in fact, the result, the way how we got it, that the limit shape satisfied this nice PDE, that was a limit as something discrete, which we found in the stochastic six-vertex model itself. There is something called, we'll call it four-point relation, namely for the expectation of the q to the h, where h is just a discrete height there. There is a relation which connects this expectation in four adjacent points, which form a kind of small rectangle. So there is a, I think it's a miraculous equation. We only found it for these free boundary conditions, and we spent some time trying to see whether there is some straightforward generalization for other types of boundary conditions, but we could not find it at that point, and I think it will be very interesting to find it. But then this equation allows us to find equation in the limit for our limit shape. Let's actually take a look. What this gives you. So what are these height functions? So this is my first simulation. So here for the boundary conditions, I used, well, if you can call it step, or you can call it semi-free domain wall boundary conditions. So what's happening is that along this direction, no paths enter. So the height function is completely flat, 0. Well, along this direction, on every location, there is a path entering. So the height function is growing linearly, which counts the path. And so these are the values B1, 0.9, B2, 0.95. And so here is what you get here. So that is a profile. This is your, this is a graph of the height function. So you can see that really the paths, well, they kind of have these rare turns because we force them to have that by having the weight going to 0. But these turns still happen. So these C-type vertices, they don't disappear completely. They are still there. It's just there are less of those vertices than the vertices of other types. Now it's kind of interesting to see how the density of these rare vertices, how does it look like? So here are for the same boundary conditions, so there are two more pictures. So these are densities of C1 vertices and C2 vertices, and the colors correspond to where the values are higher. And so, yeah.
These are simulations. Do you have, there's supposed to be some analytic function which describes louder?
Yes, so as I said,
Maybe you can repeat the question.
Right, so the question is whether we have explicit formulas for that. So I said, you can write this in terms of solution of this equation, and 2 slides later I will show you how to solve this equation. There is explicit formula how you solve this equation.
Why are we seeing the actual analytic function then? Or the actual
I don't know. I wanted to show you simulation here. In the next part. Actually, my talk has 2 parts, and one of them has only simulations, while the second part has only analytic expressions. And
it's pure and applied, man.
Yeah. So this is a simulation, and it's actually not so easy. You need to wait a little bit to get a good simulation here, because you see here, to get this plot, I averaged over 10 to the 5 simulations. And still you see that it's a little bit shaky, right? It's not completely smooth. And the reason is that, well, what's really I'm doing here? So I'm taking my configuration. It has some C1 vertices. I kind of record 1 at position of each C1 vertex, right? And then I do it 10 to the 5 times, and then I average over all the results. But you're averaging still 1s and 0s, and eventually you want to get a number which is like very small, like 001, right? And really you need to average a lot of these 1s and 0s to get good approximation of these small numbers. So it's, but anyway, that you can run on the computer and you get these interesting graphs. Well, so that was the simplest boundary condition. Let's go to something a little bit more exciting. So for these next boundary conditions, what's happening here? So here the paths are entering, not entering here, and then start entering. So the kind of this part of the domain is split into 2 segments, and the height function is growing here and not growing here. So nothing here, then paths. And here, just by symmetry, so again, there are paths here and no paths there. So that's a different boundary condition, and here for fun I choose other values of B1 and B2, but again, C's are very small. And so that was a height function, some interesting shape. And here are the densities of C1 and C2 vertices. So again, there are some interesting surfaces here. And now I want to emphasize for you one feature of these things. So you see that there's discontinuity in these densities, right? So here the density is quite large here and then very small here. Go here and again jump here. So of course, our boundary conditions also had discontinuities because I was telling you that there were paths entering here but not here. But what's happening is that in this situation of this model, no smoothing happens. So you had these discontinuities in the boundary conditions, and it kind of propagates through the system. Discontinuities live there. And if you want, that's a property of hyperbolic partial differential equations, because if you have other types of partial differential equations, maybe you have, parabolic partial differential equation, then even if you start from something non-smooth, it will become smoother and smoother very fast. Well, for hyperbolic partial differential equation, that is not happening. So, you start with something discontinuity, and this discontinuity will survive. And this will kind of important. I think that makes it interesting. It makes it somewhat different from, for example, those limit shapes which Alexei was speaking about on Monday morning, because there, for the dimers, you will never see anything like that. So, for all these graphs that Alexei was showing, the density will always continue. You could have, higher order discontinuities, like, maybe in derivatives, but not in the densities themselves. Okay, now these densities, these discontinuities, how they show themselves in the formulas. So they show themselves in the formula for the solution of this equation. So if you, just an abstract way, if you want to solve this telegraph equation, so just, you are given this partial equation and partial derivatives, and you are given two boundary conditions, what's happening on the x-axis, what's happening on the y-axis. So how would you find a solution? Turns out that there is an explicit formula. Turns out that there is an explicit formula for this solution in terms of something which is called in the literature a Riemann function. And in this situation, I like contour integrals, so I like it. I write in terms of the contour integrals, but you can also rewrite it in terms of some other, special functions if you prefer. What's important is a function of 4 variables, very smooth, nice function of 4 variables, and then your solution at general point is obtained by integrating your boundary conditions against, these functions. So where this preservation of discontinuities, where is it coming from? Well, it comes from the fact that here we have derivative. So there's a boundary condition, but also derivative of this boundary condition is entering. Here is another boundary condition, but also derivative of this boundary condition is entering. So if you had some, maybe some jump in the boundary condition, then this derivative, you need to interpret these as a delta function, and this delta function will create some jump inside the domain after you compute these integrals. So in this way, you can see from the solution that yes, these discontinuities, they remain. Yes?
Do those discontinuities propagate all the way through to the other side, or do they disappear at some point?
Well, the point is that in fact here, in a sense, there is no other side, because I said these are free boundary conditions. So you can actually embed this into the whole quadrant, and these communities will kind of become smaller and smaller until at the infinity they disappear. And you can kind of see it already here, right? It started to be huge here, but clearly this continuity becomes smaller and smaller, right? Okay. So first conclusions from what we've seen so far. So, there are these non-trivial but computable limit shapes as C1 and C2 go into 0. They solve hyperbolic PDE. But in order to be able to deduce this PDE, we very significantly use these free boundary conditions. And as I told you, the way we use it in actual proof is because we have this 4-point relation, and we only are able to produce this 4-point relation with free boundary conditions, and we don't know how to do it with other boundary conditions. Okay, so that was the result from 5 years ago, but over these 5 years, I was interested, can you do anything like that with fixed boundary conditions? I was very happy when recently, we started having progress for these fixed boundary conditions. So let me try to tell you what we do here. So now we'll switch to a slightly different setting. The feature will be still the same, that C1 and C2 will be going to 0, but the setting will change a bit. So we again deal with n times n square. So we will split this square in some possibly uneven k times l rectangles. And then what we will do is that some of these rectangles will remain in our domain, and some of these rectangles will be removed from our domain. So the domain will be n times n squared from which you remove some number of rectangles. And the way we'll be encoding which rectangles stay in the domain and which rectangles are removed from the domain will be as follows. We'll have a matrix I, maybe better say array I, of say size k times L, which is filled with zeros and ones. And if you say 1, then you keep that rectangle. And if you see 0, then you remove this rectangle. So for example, here, this is k is equal to L equals to 1. So just a single thing, and we keep it. And then, well, that's a square. And if you have here on the right, so I have n times n squared split into 9 rectangles, 3 times 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And I have a matrix I which have 2 zeros in 2 corners. And I remove these 2 things, like the parts corresponding to 2 zeros. Yes?
To be certain, it's always simply connected, right?
Right. Moreover, there will be additional restriction for this matrix I. So throughout my talk, the running restriction will be that this matrix I is obtained in the following way. You start with all ones, and then you remove like 4 Young diagrams in the corners. So if you want, this matrix I has some convexity. So if it has 1 at 2 position, then it have entire segment between these 2 things is also filled with 1. So yes, in particular, it is simply connected. Now, the boundary conditions will be as follows. So the paths will be entering everywhere from the left, and they will enter and they'll be exiting from the top. So when you enter on the left, in fact, you enter for the first position on the left where your domain starts. So they enter here and here. And similarly, when they leave from the top, then they leave at the first position where the domain ends. Right? So in particular, if you have 1 times 1 thing, then it's just the same domain wall boundary conditions, which you saw previously. And now there is a kind of domain wall boundary conditions, but in smaller domain, in which we removed some number of these rectangles. Okay. So for each configuration like that, we can associate height function just exactly as before. Nothing changes. So you have your configuration of paths, and height function changes by 1 as you move. And so here are 2 examples. It is the same type of domain as in the previous slide, and here is a slightly different domain. Now this is a matrix with 2 zeros in the corners. So you remove this rectangle, and again you look at this domain. So this is quite a rich situation, very many domains, right? Because you can have these matrices of arbitrary size. You can remove different parts of it. So there are lots of different boundary conditions which can be encoded in this setting. Okay, now I call it permutation setting. So where are the permutations here? So this is something which will be happening, and this will be a significant simplification, which is kind of guaranteed by our setting. So we will take a limit C1 to C0 going to 0. So these corners will be rare. But now there will be difference from what we saw before. So previously, this limit was happening simultaneously with size of the domain growing. Now we'll do it the other way around. So we'll first send C1 and C2 to 0. So first we'll kind of freeze things by forcing small number of corners. Now, of course, if C1 and C2 goes to 0, then the configurations, they just want to have a minimal possible number of corners. But luckily for us, this number is not 0, because if it was 0, then it would be boring. But that is something which is guaranteed by our boundary condition, that actually the minimal possible number of corners is actually n. You can have exactly n corners, and what will be happening is that in the limit you have configurations will have no C2 vertices, so those corners will just disappear entirely. But the corners of the first type, C1 type, there will be exactly n of them. So these configurations which you will get, if you want, you can encode them by permutations. Because what will happen is that in each row, in each column, you will have exactly 1 corner of type C1. So they will form collection of points, m sigma of m. And what remains out of the 6-vertex model from which we started from? Well, what remains out of the 6-vertex model is the measure which you get on these permutations. And this measure turned out to be the famous Mallows measure. Namely, turn out that each permutations will be weighted as q to the number of inversions in these permutations. And q is related to all other parameters in a simple way. This is b1, b2 divided by a1, a2. Now, I should emphasize here is that this is not the usual Mallows measure, but kind of restricted malloc measure, because not all permutations can appear, right? So in terms of the permutation matrix, we don't allow these corners to be here or there. So if you want, these are all permutations which you prohibit your permutation matrix to have entries, in some parts of the square. Okay, so that's a model which we got through the limit from the six-vertex model. And now we can ask the same questions as before about this thing. So, you will send n to infinity, keeping fixed your array I, and the sizes of the rectangles will just grow proportionally. So maybe you have 1 million times 1 million here, and this is 1/3 of the length, 1/3 of the length, 1/3 of the length. And then you ask yourself, what is the limit of random height function of this restricted malloc permutation as n goes to infinity? And you will need to tune parameter q a little bit. So you will actually need to say that it's exponent of minus r over n. So this q will need to go to 1. Otherwise, the limit sheet will be very boring. There'll be nothing interesting there. There'll be this tropical limit, which Alexei was mentioning. And if you want to have something richer than just tropical limit, then you need rescaling that q goes to 1. Okay, so what is a large n limit? So the first result which you can prove about large n limit, there is some form of variational principle for this model. So n goes to infinity, q goes to 1. What's happening with the height function? Turns out that if you want to compute probability that your height function approximates some limiting profile, small h, then this probability is approximately n times double integral of certain expression, which you can call surface tension. And this expression involves term which looks like a classical entropy. So there's something times logarithm of this expression, and additional terms like hx, hy, which are similar to what we saw in the first part of the talk. So this variational principle, we have it in our paper, but in fact, many people looked at various variational principles of the permutations, and somehow all these variational principles are proved exactly in the same way. So I don't claim much of novelty here. Of course, setting model, that was a novelty, but once the model is set up, developing this variational principle, it's not that complicated. And here are some of the people which worked on that, including some of the audience. And if you also worked on that and I forgot you, just let me know and I will add you here. Now, one thing that I want to emphasize here, that of course we know that, for example, in dimers there is also a variational principle. But in dimers, variational principle will come with different exponents. So in dimer, there will be n squared here. While in this model related to permutations, it's n. So the variational principle lives on different scalings between these two models. Okay, so now you have variational principle. Now, given variational principle, what you need to do, you need to analyze this functional, and you need to find maximizers of this functional. So corollary will be that if you assume that these functional on continuous functions, if you assume that it has a unique maximizer, then you can say that your random height function will converge to this unique maximizer. I would like to warn you that here is something which again differs from the dimer model. That in dimer model, these functions which you use, they were all convex, and because of that, it's automatically we have a unique maximizer. Here, there is not a convex functional. At least at this point, we haven't found any way to say that it's convex. Maybe there is some tricky way to say convexity, but we haven't found. From the naive point of view, it's not convex. So we don't have any kind of abstract uniqueness theorem. So you need to know that you need unique maximizer in order to analyze what's happening here. And of course, when you do this maximization problem, you should take into account all the boundary conditions. So what are they? Well, first, we know how the heights grow along the boundary, right? Because these were our deterministic boundary conditions. In addition, you will have an interesting condition that the partial derivative hxy should be 0 outside the domain. So it should be 0 in all these rectangles which are removed from this domain. Why should this partial derivative should be 0? Well, that's actually because, this partial derivative. So if you have a limiting height function and you compute its mixed partial derivatives, then what is the geometric meaning of that? Well, that's actually nothing else than the density of these corners, of the C1 vertices. So you can convince yourself, if you compute, mixed partial derivative, well, along maybe 4 squares, then it exactly counts, whether there is a corner like that here. So in terms of this corners and their densities, you can restate your problem, restate your variational principle. So if you say that you look at the function g, which is mixed partial derivative of function h with minus density of C1 vertices, then the conditions on this function g is that, okay, you should get a maximum here. And in addition, this g should vanish outside the domain. And finally, this g should be what's called permuton, namely the integral of this g along each horizontal section and along its vertical section should be equal to 1, which of course is just a manifestation of the previous thing that we had this permutation matrix which has exactly one non-zero element in each row and each column. So asymptotically, this turns into this limiting condition. Okay, so now that's a variational problem that you are solving.
Could it be
Well, I will say a little bit about convexity, the minimal result which we have, but that's all I know. Okay, so now you try to solve this variational problem. That's the next step if you want to find your limit shapes. So, well, you can start with the Euler-Lagrange equation. And turns out that Euler-Lagrange equation will be Liouville partial differential equation. So that will look as follows. So the logarithm of this density, if you look at this mixed partial derivative, then minus twice r times the density itself is equal to 0. So interestingly, today, we've seen Liouville partial differential equation already in somewhat related settings. So, Philippe was also dealing with the six-vertex model, but for different quantities there. So I don't know why. That's a result of computation that appears in both situations. But I think it will be very interesting to try to discover, why this Liouville PDE is happening here in both situations. Now, there is one feature here which I already said about in the first half of the talk, is that we expect some discontinuities. And if you expect some discontinuities, that's a little bit dangerous to write an equation in terms of the partial derivative, because if there are discontinuities, what does it even mean to differentiate your function? So it might be a little bit better to write this partial differential equation in terms of an integrated form. And in integrated form, it again will turn out to be some kind of a 4-point relation. So there'll be some relation which connects values of your function at density function at 4 points, which are kind of 4 vertices of a rectangle. And then logarithm of this will be given by the integral of the function itself over these rectangles. Okay, so you write it like that exactly because you expect discontinuities. And so this have a chance to give you a complete description of your thing. Okay, so that's an equation that you will need to
Nothing particular, you expect that this cross ratio is continuous.
Well, in all the examples that we could compute, it was continuous.
Right, because the second term is continuous.
Right. Well, I mean, something can go wrong if there are zeros here, right? If there are if g is 0, then maybe taking its logarithm is not that great of an idea. So again, the density is not continuous, right?
Right. But what I'm puzzled of is that the second term is just
right. So I will explain to you how this works. But you can already see, imagine that, when you cross some vertical line, your g is multiplied by a constant. Then it's fine. Then this ratio doesn't see it. And that's essentially what is happening in this system. Okay, so let me show you some pictures. So this is the first one. So this is a situation where you have a I matrix of size 3. So it have 2 zeros and 2 corners. So on this picture, these are, I hope that you can understand. So this is the zero density in this corner. That is kind of 1/3 of your square. So it has zero density. And there is another part with zero density hiding there, another third. And here is this r equals to 1. And so here is a graph. There are kind of these 7 parts of this thing, which are shown in this picture. Maybe that is not as clear, so it becomes a little bit better if you increase r, so make your measure less uniform. So that's what's happening here. So there are this part which grows like that, and 3 other parts. So you see that your domain got split into 9 pieces, and you have these parts of your density, which are given kind of nice and smooth and in fact even analytic things in each of the pieces. And then there are discontinuities, so they are glued. Different pieces are glued with discontinuities. So here's another example. So now matrix A will again have 2 zeros, but now in the two other angles. The value of r, again, I start with the same. So I start with r equals to 1, where these things are kind of flat. And then I start growing this r for two more simulations. So this r equals to 2. So you see that's kind of the domain, the surface becomes more interesting there. And then r equals to 5. So it will become even more extreme. So it kind of becomes like that. So r is positive. So q is smaller than 1. And this means that your permutation kind of wants to stay close to the identity permutation. And that would kind of creates this thing which is large along the diagonal. OK, good. So now, how do we find these surfaces? Like, what is that? So as I told you, that is not a simulation. And in fact, in this model, I don't know how to do good simulations. So if somebody can tell me how to do good simulations, that will be great. I don't know. That's why instead I drew these analytic things. Now, how have I found these analytic things, and what are they? So I will give you some ansatz which you use in order to find maximizers in this situation. So first, let's parameterize our problem. So what do we have? We had these prelimiting rectangles, which turn into a limiting rectangle. So you have a square, which you can have 0, 1 square, which is split into some number of rectangles by points x0, x1 up to xk, and by points y0, y1 up to yl. So it's split into these rectangles. Some of them remain. So array I fixes which of those remain. So you're only solving your maximization problem inside this domain which remains there. And so that's your problem which you're solving. Now, first, some theorem which tells you that if you manage to solve some PDE type problem, then you actually found the maximizer. And that's a tiny bit of kind of convexity type thing that we have. So imagine that you found that if you take function g of the following form, so this function g will be dependent on two functions of one variable, phi and psi. And if you do the following things with them, so you take derivative of phi, derivative of psi, and you divide by phi minus psi squared. So that's an ansatz in which you search your function. And imagine that you found g of this form such that it satisfies this constraint. So it satisfies the constraint that the integrals inside the domain of this function in both vertical and horizontal directions are all equal to 0. And in addition, suppose that this function didn't have any explosions, that it's bounded away from 0 and from infinity. Then I claim that if you manage to do that, and if in addition you know that r is small, then I could claim that this function indeed gives you a maximizer. So the way I use kind of pseudo-convexity here is that with r is small, then this term, which leads to non-convexity, is also small. And if you know that your densities are not exploding, then you control everything. And then you can say that, OK, then this gives you a unique maximizer. Now, for large r, I actually don't know. So I don't know, maybe there are more than one maximizer. What's happening there? It's unclear. OK, so now, anyway, at least for the small r, now our problem reduces to trying to find two functions, phi and psi, such that if you produce this function of two variables, g, out of them, then its integrals along the vertical and horizontal sections will be all equal to 1. So that's the problem which we are now solving. And so now I will tell you how to solve this problem.
So for different r, you get different maximizers.
Yes, maximizer depends on r, of course. Well, these pictures, they clearly depended on r, right? So the maximizer is a function of r. So the statement here is that if you fix two constants c and c, then depending on this constant, there is a small kind of cutoff that for r smaller than cutoff, you can find solutions in this form.
But what is the logic of these ansatz? How do we know that it should be like this?
Again, so if you find it, right? So I will now show you how to find this function.
Right, but you somehow arrive to these ansatz from somewhere.
So these ansatz, this just comes from the Liouville equation.
Oh, okay.
For the Liouville equation, that's an equation which people studied for 100 years. So many people were, there's different, it's kind of interesting. If you try to Google Liouville equation, you will find several articles which will give you what they call the most general solution of this equation. And each article will give you another most general form. So this is one of these articles, one of the forms which is claimed to most general, whatever that means. But I want to emphasize that this form does not imply any continuity, because like phi prime and psi prime is allowed to have discontinuities here. So it still can and it will be discontinuous, actually. Okay, now how do we solve this thing? How do we find the function of this form which satisfies this constraint? So I'll give you an algorithm now, and I will not give you I don't have time to give you a proof that this algorithm works, but you will need to believe me on that. So for this function, we will do in 2 steps. And both steps will be, we'll be solving certain algebraic equations. So in the first step, we will find these functions, phi and psi, at the endpoints of the segments. So phi we'll define it at the point x0, x1, x2 up to xk, and psi will define it at the point y0, y1 up to the top. So on this kind of grid of points, that's the first task, we will define it there. Okay, so it turns out that in order to find this function on this grid of points, you need to solve k plus l polynomial equations. And these polynomial equations are kind of interesting. At least I enjoyed looking at them. So for each rectangle, there will be 2 values of y involved and 2 values of x involved. And you will be evaluating your functions at corresponding values. So you get in 4 values altogether. And out of these 4 values, you create a cross ratio. Now, this cross ratio, you will be multiplying several of these cross ratios. But you multiply only those which correspond to the rectangles which are inside your domain. This is this power iij. So if it's 0, then the factor just is not there. And then the condition will be that the products of this cross ratio along each vertical, it's fixed to be some constant. And along its along its vertical is fixed to be some constant. And along its horizontal, each horizontal is also fixed to be some other constant. And the value of r enters only into these constants. So that's only here where r is important.
For discretization of the problem, right?
Right, this is some kind of discretization of the problem, right? So, let's discuss a little bit of these equations. So, first of all, there's like k plus l equations, and we're trying to define here how many numbers. There are k plus 1 numbers here and l plus 1 numbers here. So altogether, there's a k plus l plus 2 variables, which we're trying to find from k plus l equations. So the numbers a little bit, there's a slight mismatch. So let me discuss with you why is it happening. First, one equation is redundant, because if we multiply all these equations over all i's, then it's exactly the same as multiplying all these equations over all j's. So there's, in fact, k plus l minus 1 equations. And then in addition, all these equations actually have a 3-dimensional group of symmetries. Namely, if you replace phi by this transform, by Möbius transformation, and you replace psi by exactly the same Möbius transformation, actually nothing happens here. So the equations remain the same. That is a famous theorem from geometry that the cross ratio is unchanged when you do Möbius transformation. But actually also our density G, it's also unchanged, because you can check that this formula, this function is actually unchanged if you do Möbius transformation. So because of that, it doesn't matter. You can fix, if you want 3 parameters however you like, and it doesn't matter for our problem. And then things start to matching, because, k plus l plus 2 minus 3, that's exactly k plus l minus 1. So these equations, they have a chance of having a unique solution. Okay, so once you found the solution to this discretization of your equation, now you're in good shape, because now you do second step, where you solve another set of algebraic equations, where exactly the same double ratios entering, but now one of the variables is not an end point, but some middle point. But again, that's actually an algebraic equation in terms of e to the rx. So this is an algebraic equation of e to the rx, which allows you to find phi of x in terms of it. And similarly, there's another equation which defines e to the ri. So that algebraic equation in terms of psi of I. And so you find psi of I as a function of e of r to the y. These equations will be different in each rectangle. So that's why the solution is kind of glued from these analytic pieces. So each of the rectangles, you solve this system of 2 algebraic equations, you find solution. But on different rectangles, the solutions are different. Okay, so the theorem, which we have with Rick, is that this two-step algorithm outputs a solution of the Euler-Lagrange equation for the maximization problem. And then you use the theorem which says that the solution of Euler-Lagrange equation is actually a maximizer, at least for small r. And that's exactly how I drew those pictures for you. So that's what was happening here. Now, I emphasize, OK, first, any questions on this step or in the previous step? So there are these nice polynomial equations, which we then solve.
Where do you need this r to be small?
Right. So let's, well, from the variational principle, we needed to guarantee uniqueness of maximizer, right? That's the reason why. So it's very possible that actually the same algorithm gives you a solution for OR. So we don't have any positive or negative result here. Just in our proof currently works for small r. But let me explain to you that actually when r is extremely small, if it goes to 0, then the problem becomes even, in a sense, even more interesting, or in other sense, it becomes much simpler. So what is the simplification at r equals to 0? So these two steps both become much, much more straightforward. Maybe let's start with the second step. So it turns out that the second step, well, once you found the values of your function at the endpoint, so inside each of the rectangles, your function is actually constant. So that makes it much simpler. So you don't need to do much. Once you found it at some endpoints, you reconstruct it everywhere else as constant. So that's easy. Now, how do you find this constant? So now, for example, here you need to identify 8 constants here. So it turns out that these 8 constants are now found as simpler, still algebraic, but much simpler equations. So these equations in slightly different maybe notation can be written in the following way. So you have your matrix I made out of 0 and 1s. And what you need to do, you need to find 2 diagonal matrices, lambda and mu, such that if you multiply your matrix I on the one diagonal matrix on the left, another diagonal matrix on the right, then the resulting matrix has prescribed column sums and row sums. And this column and row sum, they are just coming from this, from the lengths of these segments. In particular, if you have kind of these all equally spaced things, and after some rescaling, what you are doing, you have given a matrix, and you need to multiply it by 2 diagonal matrix so that it becomes bistochastic. Now, this turned out to be a very famous problem in statistics, computer science, and applied math. And there is a very efficient algorithm here, something called iterative proportional fitting algorithm, which essentially what it does, first you multiply by something on the left to have one set of constraints, maybe column sums, and then you multiply it on the right to have second set of constraints, row sums, and then you iterate. You kind of update matrices on the left, on the right, on the left, on the right, and it turns out that this iterative algorithm converges extremely fast, and then you get in solution of this problem, and then you immediately get in step 2. So in that sense, equations are still there. Like if you just write these down, there are still some quadratic equations for these lambdas and mu's, but there's a very nice algorithm which always works there. And in the full case of finite R, it is a more complicated thing. Okay, let me mention some of the further direction, things we actually are thinking about, but we don't have a good progress yet. So R far away from 0. Maybe there is some transition. Maybe there is more than one maximizer. Maybe everything looks completely different. We don't have any answers at this point. Very interesting question, how to sample these things. So it turns out that these restricted permutations appeared in the work of Percy D. Konis, his co-authors and collaborator and students. And they have some motivations from statistics, so that's why they wanted to sample these restricted permutations, and turn out that when r is equal to 0, then you have uniform measure, that's kind of straightforward how to sample these things. While when you have a mallows measure, well, you can still develop some Markov chain, which hopefully mixes, but it mixes quite slowly, so that, for example, I tried to run it. I wasn't able to produce pictures of the quality which would be satisfactory for showing to you. So I think it's very interesting to find any particularly efficient algorithm to do sampling in this situation. Now, you can try to go to more complicated situations, to more complicated matrices I. For example, this is answering what Dimo was asking, does it have to be simply connected? So the matrix, this is a simple case of non-simply connected matrix, right? It has 0 in the middle and 1s all around. Now, this is a little bit unnatural for the 6-vertex model, because for the 6-vertex model, what it will be saying to you is that here in the middle, you should have no corners, but the paths can still go through it. So you will not be able to put other boundary conditions. So for the six-vertex model, this is unnatural. But from the point of view of random permutations, this is a perfectly natural question to ask. And you can ask, what is the limit shape in this situation? Now, what we discovered is that those algebraic equations which I mentioned to you, they need to be supplemented to something else. So there again will be algebraic equations, but even more complicated. And we're in progress trying to solve these even more complicated equations. Haven't succeeded so far, but this is kind of a finite task. You have some equations, you need to solve them. OK, so let me summarize what I was speaking about. So what we discovered is that six-vertex model has some intriguing asymptotic behavior in the regime when the C1 and C2 parameters go to 0, and all other parameters go to 1. So the delta approximately becomes 1 as size goes to infinity. So the solutions are related to, limit shapes are related to hyperbolic PDEs. And in some situations, they're actually piecewise algebraic, which is good. There are some unusual features if you compare those with maybe dimers or free fermion point of the six-vertex model. So we see some discontinuities, and we see some unusual scalings. So I think there's a very rich material for future discoveries. And for 2 more simulations, slightly different situations. And that's it. Thank you.